Welcome to the Crazy Hat Chemist. So another video in bonding and molecular structure. So let's get moving. Bam! So today we're talking about molecular dipoles and polar molecules. Little introduction here. So a dipole, as the name suggests, of course, has two poles to them. A positive end and a negative end, just like a magnet. There's a magnet, a bar magnet, if you will. There's a positive end and a negative end to this. A dipole can be drawn to represent the charge distribution in a polar covalent bond. We talked about those polar covalent bonds earlier, so review that. Which is a bond, that polar covalent bond, which is a bond of an unequal sharing of electrons. And it's characterized by a difference, that is a difference in electronegativity between 0.4 and 2.0. So look at that magnet there, and I'm drawing a dipole moment. That is, there's a positive end and a negative end. Think about it this way. If I had a bow and arrow, and then I let it go, and I hit you with my arrow, you would be hit with the negative end of that arrow. That's the pointy end. That's why it's the negative end. That's why it's negative to you. But it's positive to me, because I can see that I've hit my target and the feathers are sticking out. That's positive. So the point of the arrow is going to the negative end. The feathers to the arrow are going towards the positive end. Okay, here's a molecule right here. When there's a charge distribution, an unequal sharing of electrons, you can write this as a delta positive and a delta negative. That's the same thing as writing that dipole moment. It's the same thing. One doesn't have to be bigger than the other. I just differentiated them. Okay. All right, so in order for a molecule to be polar, two criteria must be met. Number one, you must have a polar covalent bond. That's a large difference in electronegativity between 0.4 and 2.0. That's not that difficult to come by. And two, you must have an asymmetric molecule. If you looked at the previous video, we talked about molecular geometry and asymmetrical molecules. Some of those molecules are just asymmetrical and they're polar by definition, period. Okay, so here are a bunch of molecules and you can draw their dipole moments. Notice that this is just a mixture of molecules and nothing's happening to them. They're rolling about each other. But if you want to apply an electric field to these molecules, then all these molecules will align themselves up, just like the bars of a magnet will line themselves up so that they're all in the row. That's the positive, negative, positive, negative, positive, negative. Okay, all right, hopefully that works well for you. Don't worry, there's some cool chemistry jokes at the end of this video, so hang on to that. We are not done. A consequence of bond polarity is seen in the HCl molecule. That's hydrochloric acid with an AQ there. Okay, HCl is polar since there is a large difference in electronegativity between the hydrogen at 2.1 and chlorine at 3.0, creating a positive end that is an unequal sharing of electrons, and the molecule is asymmetric. So the positive end is at the hydrogen, the negative end is at the chlorine, because chlorine is more electronegative, so it's going to draw the electrons within that bond towards itself. Okay, that's that asymmetry in bonding. Okay, due to the bond polarity, HCl bond energy is larger than expected for a pure covalent bond. Okay, a pure covalent bond for HCl is 339 kilojoules per mole, whereas the measured value for the actual HCl bond is 432. So that means that that bond has increased in energy due to the electronegativity difference. Okay, the difference is 92 kilojoules. This is due to the difference in electronegativity. Okay, so hopefully that makes sense for you. Here's some polar humor here for you. That's right. If both a bear in Yosemite and one in Alaska fall into the water, which one dissolves faster? Ah, the one in Alaska, because it's a polar bear, of course. Ah, okay, here's one more. Okay. What do dipoles say in passing? So you're passing a dipole, walking down the street, passing a dipole, and what do they say to each other? Hey, have you got a moment? All right, so that is another Crazy Hat video from the Crazy Hat Chemist, and the crazy hats all over, especially at my school, will enjoy this hat. Gotta love this hat, right? Go Raiders. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Pass on my YouTube channel to all your friends. The Crazy Hat Chemist. Yeah, baby.